All right, so we're starting on page 20. So today we're talking about arithmetic sequence. There are many types of sequences, but there's only one that is related to linear functions. And in fact, it is the type of discrete linear function. I know that my screen is different. It's frozen. I'm going to fix it. So I want you guys to underline that word discrete linear function. Underline that discrete linear function. I want to talk to you about that. So when we have something that is discrete, when we talk about a discrete linear function, what we're meaning is that we only have points on our graph, even though it's linear. Even though it's linear, we only have points. No line. Again, let me say, even though it's linear, we only put points on there. Why is that? What did we learn yesterday about sequences? What kind of numbers do sequences use? Yeah, sequences don't include decimals. So if we use that line, it includes decimals, right? So a sequence can't have decimals. It can only have points, right? Okay. So Evan is saving money to buy a new toy. She already has $12 in her account. She gets an allowance of $4 per week, but she only plans to save 3 of it. So she's saving 3 of it. She started with 12. So after the first week, when I let n equal 1, she has $15. Well, that makes sense because that's 12 plus 3, right? After 2 weeks, how much money does she have? Because that makes sense because 15 plus 3 is what? 18. So what are we doing each time? We're adding 3. So let's fill out our table. So if I add 3 every single time, after 3 weeks, I'll have how much? 21. And after 4 weeks, I'll have how much? 24. And after, yep. 30 and 33, you said? Okay. So it says, what's wrong with the graph? I know we haven't done B yet, but I want to stay where the picture is. What's wrong with the graph of the sequence that's shown below? What's the problem with it? It's got a line, right? Are we allowed to have lines? No, this is not discrete. So we're just going to write that this is not discrete. And then I'm going to put a little star and say that we cannot connect the points with a line. So if we connect the points with a line, then we're not using natural numbers as our input values, 1, 2, 3, 4, 5, right? We're using decimals and fractions. It says write a recursive definition. Write a recursive definition. So if we want to write a recursive definition, we have to start with the initial value. What is the initial value of my function? What is a sub 1? What is a sub 1? It's 15. The initial value is 15. So then I say, well, that means that a sub n equals, what is the term that came before a sub n? How do I show that? How do I show this term that came before a sub n? Nope. Subtract what? Subtract. I want the term that came right before n. The one that came right before it. How much are we subtracting? 1. A n minus 1. Guys, we did this yesterday 100 times. A sub n minus 1. So I'm going to take the term that came before it. That's what a sub n minus 1 stands for. And what am I going to do to it? Add what? 3. So we're not understanding this recursive definition. You guys are really struggling with this. So here's what I want you to understand. If I wanted to find the fifth term, the a sub n minus 1, that's the fourth term. 5 minus 1 is 4. Take the fourth term and add 3 to it. That's what this is saying. If you want to know what the fifth term is, you have to take the term that came before it, the term that came right before it, the number in the fifth term minus 1 is the fourth term, and add 3 to it, okay? So every single time you use a recursive definition, you're going to start with the name of your sequence, a sub n, m, a sub m, whatever, b sub n, and then the equals is going to be whatever that name of your sequence you're using, a sub n minus 1, because you want the term that comes before it. And then whatever you're doing, adding or subtracting in your value, okay? So the second part of this, D says, Evan proposes that the following explicit formula for the amount of savings. So this is the first time that we've seen this. So I'm going to kind of box in the word explicit formula. An explicit formula is written in the form y equals mx plus b. That's what explicit means, because this is remember we said an arithmetic function is a linear function. So the explicit formula is written in y equals mx plus b. So she's saying that her explicit formula, a sub n equals 3n plus 15, stands for however many weeks she saves. So let's figure out what happens if she saves for 4 weeks, because that's a value in our table. So if we let n equal 4, that means a of 4 equals 3 times 4 plus 15. But 12 plus 15 is 27. And how much money did she have saved in week 4? She had 24. So is this the correct formula? No. So this is not correct. This is not correct. Someone tell me why this is not correct. And I'm going to go to the graph. Why is this not correct? What does the value of b represent in the term y equals mx plus b? Guys, we've been using that forever. Don't look at the equation. Just tell me what b means in the form y equals mx plus b. What does b stand for? Yeah, b is your y-intercept. B is your y-intercept. And when does your y-intercept happen? The y-intercept happens when x is 0. When x is 0. Okay, but we don't use 0 for a sequence, do we? We don't let our numbers equal 0. But if I want to write an explicit formula, I have to work backwards to figure out what would happen if we had used a 0. So I'm going to go back to my table. So if I worked backwards on my table, instead of adding 3, if I subtracted 3, what would happen when I let x equal 0? What would my y-intercept be? It would be 12. So if I want to write an explicit formula, I have to know the y-intercept. So my explicit formula actually would be a sub n equals 3n plus 12. I'm still not going to be able to use 0 as a value of n. N has to be all natural numbers, but I would get the right answer if I plugged in a 1. After the first week, 3 times 1 is 3 plus 12 is 15. That's the number in my table. After 2 weeks, 3 times 2 is 6 plus 12 is 18. After 3 weeks, 3 times 3 is 9 plus 12 is 21, and so on. So this is our explicit formula. Okay, it's written in y equals mx plus b. So arithmetic sequence are the ones where the terms in the list increase or decrease by the same amount. So the terms in your list increase or decrease, just like a linear function. So they increase or decrease by the same amount. We actually call that a common difference. We call that amount a common difference. And it actually represents your slope when it's in the explicit form. So it's a common difference. It's how much you add or subtract. So it's the amount that you add or subtract in the recursive form. And it's actually your slope in the explicit form. Okay? It's your slope in your explicit form. It's kind of cool that you can have two different equations that mean the same thing. So exercise 2, example number 2 says an arithmetic sequence is given using the recursive definition b sub 1 equals -3. This means that my first term is what? What's my first term? -3. My first term is -3. What am I going to do to find the next term in my sequence? What does it say that I'm going to do to find my next term in my sequence? I'm going to add 6. So if I add 6 to -3, what do I get? 3. If I add 6 to that, what do I get? If I add 6 more to that, what do I get? 15. If I keep adding, right? If I add 6 more to that, what do I get? 21. It says, what is the fourth term? What is the fourth term in my sequence? 15. Let's count it. This is 1, 2, 3, 4. Okay, do you see it, Noah? Okay, I just kept on going to make sure you understood the pattern. I probably tricked you on that. That was not intentional. Sorry about that. Okay. So do you guys feel like you can at least look at a recursive definition, know where the sequence starts and what you're adding or subtracting to it? Do you guys see how in the recursive definition, this amount that you're adding or subtracting in the recursive, if we were to write this as an explicit, that would be my slope. If we were to write that explicitly, that would be my slope. Okay? All right, let's go to the next page. So it says arithmetic sequences are relatively easy to spot, and they're easy to fill in, so to speak, because all you're trying to do is figure out what we're adding or subtracting to get to the next term. We're always trying to figure out what we add or subtract to get to the next term. So if you look at exercise 3, it says for each of the following sequences, determine if it's arithmetic based on the information given. And if it is, fill in the blank. If it's not, you have to show why. So if it's not arithmetic, you have to show me why. Okay? So let's look at this first one. They don't go to everybody, but I appreciate that. So tell me, in this first example, am I adding or subtracting the same amount to get to each term? In example A, am I adding or subtracting the same amount to get to each term? I'm adding, right? What am I adding each time? I'm adding 4. So is this arithmetic since I'm adding something, or is it not arithmetic? It's an arithmetic sequence. Each time I'm adding 4. So what is the missing term in my sequence? It's 17. Yeah. This is 17, and I'm just going to write below it arith. I'm going to kind of abbreviate. This is an arithmetic sequence. If I look at my next term, remember, if it's arithmetic, we're only adding or subtracting something. Well, if I start off by adding 5, well, 10 plus 5 is what? 15, not 20. So is this one arithmetic? No, this is not, because we are not adding or subtracting the same number. Can you guys tell me what you're doing there to get the next term? You're multiplying by 2. What kind of a equation increases by a multiplier? We just finished that whole unit. What kind of an equation increases by a multiplier? Exponential. An exponential equation increases by a multiplier. What about example C? Are we adding or subtracting something each time? What are we doing, Amalia? Yeah, we're doing -3 every single time. -3. So what's the missing term going to be? -2. And this is an arithmetic sequence. This is an arithmetic sequence. Let's look at this next one. Are we adding or subtracting something every time? So we're multiplying by 1/4. Good job. Yeah, this is not arithmetic. Same reason, because we are not adding or subtracting the same number. Okay. These are both exponential. We just finished exponential functions, right? So those are increasing by a multiplier. Those are increasing or decreasing by a multiplier. That was that whole idea of exponential functions, right? So find a specific term in an arithmetic sequence without listing them sometimes can be a challenge. But if you take your time and really think about it, you probably can figure out what's happening, especially if you have an explicit formula. So let's consider the arithmetic sequence whose first 3 terms are given. So my first 3 terms are given: 4, 14, and 24. 4, 14, and 24. I want to find the 4th term. What is the 4th term? How did you do that? It's going up by 10. So I know that my 4th term equals 34. And I'm just going to put in little parentheses up here. We are adding 10. We're adding 10 each time. Well, what if I wanted to show it in terms of like repeated addition? So if I wanted to find the 4th term, let's see, I started with 4. And then to get the 2nd term, my beginning term, this is my initial value, right? 4. How did I find the 2nd term? What did I do to the 4? I added. And then to get to the 3rd term, what did I add? And to get to the 4th term, what did I add? So could I actually think about this mathematically as 4 plus 3 times 10? That's still going to give me 34. So it says use what you learned in part A to find the value of a to the 10th. Okay, so let's think about that. If I want to find the 4th term, I started with my initial value, and then I need 3 more additions of 10. So initial value, that's 1 term, plus 3 gives me 4 terms. So if I want to find the 10th term, I'm going to start with my initial value of 4 plus how many additions of 10? 10 terms. The first one is 4. So how many do I have left? 9. 9 additions of 10. 9 additions of 10. So can't we write it like that? Remember that number that we're adding or subtracting is our slope, right? So the 10th term is actually 94. Yeah. Our 10th term is actually 94. Okay. So for the recursive formula for A sub n based on the term number, let's see. Well, what's our recursive formula? We know that our first term, A sub 1, is what? What is A sub 1? A sub 1 is 4. Okay. So A sub n equals A sub n minus 1 plus, what are we adding each time? 10. Okay. If I want to write the explicit formula for A sub n, the explicit formula, well, my first term, 4 plus 10 times the term before it, right? 10 times the term before it. So think about what we did, because I just want to show you why this works. If I want the 8th term, I take 4 plus, so the n value that I'm looking at it is 8. But then what did I multiply by? What did I multiply my 10 by? Look up here. If I was looking for the 10th term, what did I multiply by 10? Yeah, I'm going to multiply by 7 times 10. And that's what n minus 1 is. Your n minus 1, 8 minus 1 is 7. Okay, so this is your recursive definition. Or, sorry, your explicit definition. This is your explicit. All right, seats in a small amphitheater follow a pattern where each row has a set number of seats more than the last row. We have to figure out what that set number of seats is first. It says if the first row has 6 seats, so, whoops, what just happened there? If our first row has 6 seats, so I'm going to start off with 6, and our 4th row, so we don't know how many are in here, the 2nd row or in the 3rd row, but the 4th row has 18. How many seats does the last row, which is the 20th, have in it? Well, think about what we're doing. We take our initial term, this is the first term, and we add some value, I'm going to call it x, to get to the 2nd term, plus some value to get to the 3rd term, plus another value to get to the 4th term. So I could actually write an equation that says 6 plus 3 times that magical number equals 18. So how could I solve this? How could I solve this? I'm going to subtract what? 6 from both sides. So 3x equals 12. Divide both sides by 3. And I find out x, the number that I'm adding to each row is what? 4. The number that I'm adding each time is 4. So 6 plus 4 is 10. 10 plus 4 is 14. 14 plus 4 is 18. Right. Do you guys see how that works? Okay. So how do we figure out how many are in the 20th row? How in the heck are we going to do that? Well, think about what we did before. If I want to know the 20th term, a sub 20, I start with my initial term. That's the first value. How many sets of 4 am I going to add to get to 20 terms if I already have the first term identified? How many more numbers do I have to add? 1 plus what equals 20? 19. So I'm going to have to take that and add it to 19 times. What's the number that we're growing by each time? 4. So the 20th term is 6 plus, let's see, 76, I think that is, which equals 82, right? So the 20th row has 82 seats. There are 82 seats in the 20th row.